Hi guys, this is Prashun again. I am again coming with few more problem and solutions of complex numbers. In my earlier videos, we have gone through the theory portions as well as few problems and solutions. And here we will describe few more problem and solutions of complex number. Complex number is very important as a part of WBJEE syllabus, and because you people will get lots of problems in complex number, as well as complex number problems are combined with AP/GP quadratic equations. So complex number is a little bit real scoring subject. So let's discuss with some of the problems and solution of complex numbers. So let's proceed. Example: find the modulus and argument of the complex number -1 minus I root over 3. Okay, so we'll take the we'll consider the complex number as z equal to -1 minus I root over of 3. So we know from the polar form that we are considering that r cos theta equal to -1 and r sin theta equal to minus of root 3. So on squaring and adding, we obtain r square cos square theta, that's the left hand side, and for the other expression, that's r square sin square theta equal to -1 whole square plus minus of root over 3 whole square, or r square, because cos square theta plus sin square theta equal to 1, so r square equal to 4, or r equal to 2, because conventionally r greater than 0, because we are finding out the modulus and argument. So modulus equal to 2. 2 cos theta equal to -1, because r cos theta equal to -1, so I am putting r in place of 2. So 2 cos theta equal to -1 and 2 sin theta equal to minus root 3. So cos theta equal to -half and sin theta equal to minus root 3 by 2. So it means sin is negative as well as cos is negative. So it means as both are in negative, so they are in third quadrant. So we have to find out the argument. Argument is minus of pi minus pi by 3. So that is the formula when the argument is in the third quadrant. That means minus of 2 pi by 3. So argument we have got, as well as modulus we have got. So let's move to the next problem. Convert the given complex number in polar form. Okay, the complex number is -1 minus I. We will consider z equal to -1 minus I. So r cos theta equal to -1 and r sin theta equal to -1. Because I, the coefficient of I is 1, so r sin theta equal to -1. On squaring and adding, we obtain r cos square theta plus r sin square theta equal to -1 square plus -1 square. Similarly, r square, because cos square theta plus sin square theta equal to 1, so r square equal to 2. So r equal to root over 2, as r greater than 0, so we are not considering that negative root over 2. So modulus equal to root over 2. Again, if we put r in the above expression, so r cos theta equal to -1, so root 2 cos theta equal to -1, and root 2 sin theta equal to -1. So cos theta equal to -1 by root 2 and sin theta equal to -1 by root 2. Here also we can see both cos theta and sin theta are having negative sign, so that means it is in the third quadrant. So argument equal to minus of pi minus pi by 4. So that is equal to minus 3 pi by 4. Hence -1 minus I, because we have to ultimate our intention is not to find out the argument or not to find out the modulus. We have to reduce this in the polar form. So -1 minus I equal to r cos theta plus I r sin theta equal to root 2 cos of theta, means minus 3 pi by 4. So minus 3 pi by 4 plus I root 2 sin of minus 3 pi by 4. So this is the answer, or I can further reduce it into root 2 by taking root 2 common, cos of minus 3 pi by 4 plus I of sin minus 3 pi by 4. So this is the polar form. Next example, solve the equation root over 3x square minus root 2x plus 3 root 3 equal to 0. It is ax square plus bx plus c equal to 0. So comparing the given equation with ax square plus bx plus c equal to 0, we obtain a equal to root 3, b equal to minus root 2 and c equal to 3 root 3. So the discriminant that is b square minus 4ac is minus of root 2 whole square because b is minus root 2 minus 4 of ac. A means root 3 and c means 3 root 3. So it becomes 2 minus 36 equal to minus 34. So the required solutions are, there are two solutions. One is minus b plus root over d by 2a. Another one is minus b minus root over d by 2a. So it becomes, I am putting the value of small b and discriminant as well as a. So I am just putting from above. So minus of minus root 2 plus minus root over minus 34 divided by 2 root 3 equal to root 2 plus minus root over 34i, because root over minus 1 equal to I. So I am just putting root over 34 into I divided by 2 root 3. Next example, solve the equation x square plus x by root 2 plus 1 equal to 0. We'll do in the same way. Here just the coefficient of x is 1 by root 2, that is b equal to 1 by root 2. So the equation can also be written, or in another way I can write the equation as by taking the root 2 as the entire LCM of the denominator. So root 2 x square plus x plus root 2 equal to 0. So it is in the standard form of ax square plus bx plus c equal to 0. So from here I can get a equal to root 2, b equal to 1 and c equal to root 2. So the discriminant becomes d equal to b square minus 4ac. b square means 1 square minus 4 into a is root 2 and c equal to root 2. So that is 1 minus 8, because 2 into 4 8. So 1 minus 8 equal to minus 7. So the required solutions are x equal to minus b plus minus root over of d divided by 2a. So minus 1 plus minus root over of minus 7 by 2 root 2, and minus root over of minus 7 means root over of 7i, because root over of 1 equal to I. So this is the solution. Now you can see one thing, in both the problems the discriminant is negative. So as the discriminant is negative, so both the things are coming as I, in a complex number. The required solutions are coming in a complex number. So that was the thing we have, that was the theory we have heard in the quadratic equation chapter. If you see my quadratic equation chapter, then you will be able to understand like why these things are coming as a complex number. Okay, let's move to the next problem. For any two complex numbers z1 and z2, prove that real of z1 z2 equal to real of z1 into real of z2 minus imaginary of z1 minus imaginary of z2. Okay, so let's take z1 equal to a plus ib, that is one complex number, and second complex number I am taking z2 equal to c plus id. So z1 into z2 equal to a plus ib into c plus id. That means AC plus I into AD plus I into BC plus I square BD. That means AC minus BD, because I square BD means minus BD, I square equal to minus 1, plus I of AD plus BC. So real of Z1 into Z2 means AC minus BD, because I am just comparing real and imaginary parts. Okay. Now AC minus BD means A means real of Z1, fine, because real of Z1 equal to A, because imaginary of Z1 equal to B, IB. So real of Z1 equal to A. Next one is C. C means real of Z2, fine, minus B means imaginary of Z1 and D means imaginary of Z2. So the proof has been done. we will go through another problem. If a plus ib equal to x plus I whole square divided by 2x square plus 1, then prove that a square plus b square equal to x square plus 1 whole square divided by 2x square plus 1 whole square. How to deduce these things? First write a plus ib equal to x plus I whole square divided by 2x square plus 1. Now x plus I whole square I will simplify as x square plus 2xi plus I square, and the denominator becomes 2x square plus 1. Now if I go further, x square, I square means minus 1. So I will put x square minus 1 plus I of 2x divided by 2x square plus 1. From here I will just put the real and imaginary part separate. So real part is x square minus 1 divided by 2x square plus 1, and imaginary part is I of 2x divided by 2x square plus 1. You can see the x square minus 1 in the first portion, the minus is a little bit higher, minus sign is a little bit higher because it is a PowerPoint problem. I have put minus as a prefix, not as a suffix, so that problem has happened. So this is a just printing mistake, so please read it as x square minus 1. So comparing real and imaginary part of the above expression, I know then a equal to x square minus 1 by 2x square plus 1 and b equal to 2x by 2x square plus 1. Now I will go to the proof. A square plus b square equal to then x square minus 1 whole square divided by 2x square plus 1 whole square plus 2x whole square divided by 2x square plus 1 whole square. So if I take 2x square plus 1 whole square as a LCM, my numerator will be x square minus 1 whole square plus 2x whole square. It means x square minus 1 whole square means x to the power 4 minus 2x square plus 1, and 2x square whole square means 4x square. So ultimately it becomes x to the power 4 plus 2x square plus 1 divided by 2x square plus 1 whole square. So it means x square plus 1 whole square divided by 2x square plus 1 whole square. So hence it is proved. Thank you. So we have completed 5 or 6 examples of complex number. We will work out with more problems and solutions of complex numbers in the subsequent lessons. So till now, thank you. If you like my video, please click on the like button in YouTube and subscribe me so that this video can be reached into the with the wider audience. Thanks once again and have a good day. Thank you.